let's move to the second last paper of the section, network support for scalable and high-performance cloud exchanges. Another co-author presenting on behalf of the main author, Srinivas Narayana, is an associate professor at the Department of Computer Science at Rutgers University. He researches on advances in compiler and formal methods technology to improve internet software and hardware. His research has been recognized with a Distinguished Paper Award at the Code Generation and Optimization CGO 2022, the Best Paper Award at SIGCOMM' 2017, and Facebook Networking Systems Award. And well, you got a lot of awards here.
Sorry, I'm embarrassed. I shouldn't have uploaded that.
Congrats. So yeah, the floor is yours.
Okay, thanks Simone for the introduction. So yeah, changing gears a little bit here from wide area to within cluster. So this talk is about cloud financial exchanges, right? So let's kind of provide some background on what that is first. So in a cloud financial exchange, you have an exchange server and a bunch of market participants who are trying to buy and sell various commodities. And the exchange server can release various snapshots of market data. These could be prices of commodities or trades that other participants make. And typically, these pieces of market data are broadcast to all the market participants. And then there may be multiple such pieces of data. And then participants may use this market data from the exchange or other sources to then place orders or sell other things. And those will in turn get communicated to the exchange server that matches bids for various commodities with how much was asked for those commodities. So that's kind of what a financial exchange does. So now, going beyond the price, which participant actually gets to buy or sell a commodity also depends on who asked first. So even if two orders come in asking to buy the same item, and the price on those two is close or identical, then the participant who asked first is going to be able to successfully complete the trade. So typically what ends up happening in these cloud financial exchanges is participants compete on how quickly they can produce these orders. And this places a premium on how quickly the participants can reach the exchange servers. So traditional financial exchanges that operate at high speed are built in these private data centers or co-location facilities where latency and fairness of latency across these market participants is at a premium. In fact, anecdotally, we are told that these exchanges have these glass floors where people lay out cables of equal length. So the participants can, in fact, see that the latency between their facility in the colo and the exchange is going to be exactly equalized with every other participant. Right? So that's kind of how obsessed the participants are with this criteria. So the fact that you all have to be in this kind of a facility places a huge premium on space, right? So co-locations are not cheap in this kind of environment. So you can't necessarily have a exchange which has lots of participants, maybe a few tens to order of 100, and getting a spot as a market participant in one of these co-location facilities can be very expensive for the participant, and also hosting the exchange can be very expensive for the exchange as well. So in this work, we asked this question: can we use the public cloud to scale and commoditize these financial exchanges? And previous works have actually talked about enabling certain kinds of capabilities of these financial exchanges on the cloud. But in this work, really our focus is the scale. And I'll also explain kind of what the problems are when you try to scale up these exchanges. But when you move into a public cloud, there are many benefits that come. Notably, you can kind of move away from this constraint of fighting for limited physical space around the exchange server. And you can kind of inherit the scale benefits of the cloud by having potentially thousands of traders who can all rent their virtual machines on this cloud. You can effectively now, to launch a new financial exchange or become a participant in a new financial exchange, you just need to rent a VM, or you just need to rent, as an exchange server, you just need to rent a few VMs perhaps, and that can allow you to now establish a new financial exchange. And being in the cloud provides access to various services that may not be easily available as part of a co-location. So you can have access to various kinds of analytics, data sources, machine learning, right? So you can have access to all of that. And of course, all the typical kind of benefits of the cloud come into the picture, right? Like being able to allocate resources flexibly, elastically, reducing cost, et cetera. However, there's no free lunch, so there will be trade-offs. So the trade-offs with respect to these co-location facilities is that the latencies are going to be higher. So they are not going to be this low guaranteed kind of wire length latency. And the guarantees of fairness will have to be coarser, right? So we have to adapt. So what's really the big challenge of moving these financial exchanges to the cloud? So really it is actually the high latencies and the variation in the latency. So this is actually a snapshot of a measurement that we did, the latency between two virtual machines on one of the popular cloud services. You can see a few things, actually. So there's kind of order of magnitude variation across time. And also, we don't show that in this picture, but there's actually also spatial variation across multiple clients. And this kind of a network is really, if you take it as is unfit for the kind of fair competition you want in a financial exchange. So in our work, Onyx, we present mechanisms that achieve fairness and high performance, meaning lower latencies at scale. So if you think about the existing solutions to enable financial exchanges, so you can think about the kinds of properties we want from them, right? Like we want economy, meaning it should be cheap, relatively cheap to host exchanges and the participants. Scalability, meaning you can support a larger number of participants. Performance, meaning you can reach the exchange server as quickly as possible with low latency and match orders at a high throughput. Fairness, meaning that the different participants can reach the exchange at roughly the same time. The state-of-the-art financial exchanges, which are on-premise or co-located, fall into this kind of a profile, right? Like they're really good on the performance and fairness front, but not so great on the economy and scalability front. If you look at the other end of the extreme end of the spectrum, so there's also web APIs that allow people to trade from their browser screens or by writing kind of small web applications. So they are extremely economic and scalable, but they do not provide the kind of performance and fairness guarantees required to compete in a fair and a real way at high speed. So what this work really proposes is sort of a new point in this design space where you get a bit of the performance and fairness guarantees of being on-prem with the economy and the scale of having something like a web API. So we really kind of put forward this new point in this design space. So what is Onyx? So it consists of a multicast service that's able to disseminate market data to order of 1,000 participants. And the guarantees that we want to provide are that each of these participants can receive a message within 1 microsecond of each other. And we also provide an order submission service, which can effectively provide fairness on the inbound side from the market participants to the exchange server. Okay? And it can also handle bursty traffic, so orders that are generated in response to bursty events in the market. And all of this has been prototyped on at least 2 cloud services, AWS and GCP. So we'll present results later. Okay, so just kind of the agenda for the rest of the talk. So we'll discuss what the fairness definitions are for Onyx and how we relax them with respect to on-prem. How we have fairness that is scalable on the outbound direction from the exchange server to participants. How we provide fairness on the inbound direction from market participants to the exchange server. And here we actually advocate for an application-specific or a domain-specific scheduling policy that gracefully can handle bursts of orders due to market activity. Okay, so let's dive in. So the classic definition of fairness or outbound fairness is that when an exchange server creates a piece of market data and wants to broadcast it to all the participants, these participants must receive that piece of data at exactly the same time, right? So the difference in the reception time must be 0. On the inbound side, when market participants create their orders at various points in time, the exchange server should then be seeing those orders exactly in the sequence in which they were generated. Okay? But of course, in practice, you have to kind of relax these guarantees a little bit. So we kind of say that for outbound fairness, the difference in the data reception time between two participants should be close to 0, right? Like it can't exactly be 0, so we want to try and keep them as close to 0 as possible. And we also say that the orders at the exchange should be seen in the sequence of the timestamped generation order. So what we mean by this is we need some trusted entity that can tell us that this is the time at which an order was generated, and then the exchange can be made to see those orders in the sequence of those timestamps. So our goal here in this paper is to achieve fairness while being performant at scale. Okay? And by scale here, we really mean order of 1,000 market participants. So how do we achieve outbound fairness, and how do we scale it? So in prior work, outbound fairness was achieved by this primitive called hold and release. So the idea is that you have a gateway, which is a trusted entity that fronts every market participant. And really, these gateways are at the perimeter of a trusted domain of clock synchronization. Okay, so every time the exchange sends out a piece of data, the gateways are told, hey, hold this piece of data until this time in the future, and then send it to the market participant at this point in time, right? And because the clocks are synchronized, the data will be released at exactly the same time from all the gateways. Now, the problem with this kind of a model, when you scale the number of market participants, is that just sending this piece of data to many, many gateways corresponding to many market participants already incurs a significant amount of serialization delay, right? If you have 1,000 distinct destinations to send a piece of data, just the time between when the first of those messages was transmitted to the last of those messages was transmitted is already quite significant, which means that the release time that you provide to the gateway must also be very large, and so the latency of the entire system is going to be large. Okay, so this is where we kind of have this tension between latency and fairness, so you somehow want to break out of that. So in the literature on scalable multicast, it's actually known that if you have tree-based topologies and communication patterns, it is possible for you to scale multicast much better. And this is exactly what we do in this work. So we scale this, this kind of problematic multicast by using a tree-like topology. So the exchange, instead of sending a piece of market data to, let's say, 1,000 market participants, will send only to its direct children in this tree of what we call as proxy nodes. So the number of children is much smaller than the number of market participants. So the proxy nodes can then send the data to their children in this tree, and so on and so forth, right? So this actually allows us to send fewer copies of the same data, but then reach this larger number of market participants. Okay, so but of course, adding more components in the path between the exchange server and the market participant also increases the latency and the variance of when that data will get to the market participant. So here we have a bunch of techniques that allow us to kind of handle this variance. So I won't be going into detail on each one of them, but to handle latency variance on the individual links in the path, we use packet spraying. To handle the performance variation of these proxy nodes, we use hedging, which is actually a common technique to curtail tail latencies in systems. And we also use hedging of a different form to handle performance variation in receiver VMs. Okay? So in our deployment, each market participant is effectively a separate VM. Okay? So now let's move on to inbound fairness. Okay? So here we have two kind of sets of kind of pieces to the design. So one is a sequencer and one is a scheduling policy. So let's look at them in turn. Okay? So the problem here is that you have a bunch of market participants, and the data that they send must be seen by the exchange server in the order in which, in which they were generated, right? So Previous work assumes clock synchronization and uses the component called a sequencer that effectively takes the orders that were received and holds it until a certain point in time to account for the latency between the sequencer and the market participants, and then releases them in the time-ordered sequence to the exchange server. So now, there is once again kind of a latency fairness tension here, because if you wait too long, and depending on the kind of latency between the market participants and the sequencer, it may actually be too long because the latencies may be small, but you may be waiting too long with this fixed delay. But if the latencies are long and you don't wait long enough, then that's going to result in an unfair delivery of these orders to the exchange server. Okay? So how do we get around this? So we actually leverage the fact that the sequencer knows who the market participants are. And also, we want to allow the possibility of smaller network latencies to drive faster delivery of these packets to the exchange. Okay? So what do? So clients attach a trusted timestamp of when the order was generated to outgoing messages. And the sequencer, instead of waiting for a fixed delay, waits for at least one message from each client before it sends it to the exchange server. So in this example, so you wait for messages 1, 2, 3. These are from different market participants. You have at least one message from each market participant. And then now the sequencer can release, regardless of this delay, the message that has the earliest timestamp. Okay? And then it continues to do the same thing with this backlog of messages that it has. So we also guarantee in our system that even clients that are inactive will continue to send messages just as a heartbeat so that the system can keep making progress. Okay? So one drawback of this kind of design is that liveness may be affected if clients fail. So we we treat that as a separate problem. But fairness is guaranteed if the clocks of the entity that's doing these timestamps are actually synchronized. Okay, so next comes the question of bursty orders. Okay, so turns out that doing this is not enough to achieve inbound fairness. So the problem is when you have market events that happen in a burst, like you might also have orders that are generated in a burst. And these bursts may overwhelm the ingress bandwidth of the exchange server. Okay? So any system that tries to guarantee inbound fairness must also handle this problem of bursty arrival of orders at the exchange. And because the bandwidth is actually limited, you need some way to kind of figure out, okay, how do I match the orders at the fastest possible rate with the lowest possible latency? So this is where the Onyx design includes this component called a limit order queue. So the limit order queue is a domain-specific scheduling policy that runs at the proxy nodes and the gateways that allows these nodes to prioritize orders that are more likely to be matched by the exchange server over orders that are less likely to be matched. So this actually takes into account a domain-specific algorithm that is typically used in matching bids to asks in financial exchanges. So this is the price-time priority algorithm. It's a commonly deployed algorithm that takes the bids for a commodity and the asks for a commodity and first of all holds them in this data structure called a limit order book. And anytime, so kind of the true value of this asset is effectively estimated to be kind of the mid price between these bids and the asks. And anytime you have a bid that crosses above the mid price, then that bid is likely to be matched with one of the asks, right? So this is kind of the basic intuition of the algorithm. So in this example, if you have 4 orders, which let's say a proxy node is looking at, there are kind of bids that have values of $1 and $2, and then asks that have values of $4 and $5. The intuition here is that you can prioritize those bids that are closer to the mid price and the asks that are closer to the mid price. So something that is a $5 ask and a $2 bid can be prioritized over the other orders. Okay? So this is kind of the intuition. But naively doing this sort of prioritization can actually result in violating fairness. Okay? So what is the fairness property we want? So we have a FIFO fabric. If we have a scheduler that purely just kind of sends data in first in, first out order, and the exchange can consume this stream of orders at an infinitely high throughput, then there is some sequence of orders that are eventually processed by the exchange. And processing here means you've matched the bids to the asks. Similarly, when you have a limit order queue fabric, suppose there comes in a sequence of orders, and the exchange sees them, sees kind of a subset of them, and finally produces a sequence of processed orders. What we want is these two sequences of the FIFO processed orders and the limit order queue processed orders to be the same. Okay? And this is despite the fact, or in fact, because of the fact that the ingress of orders coming in at the exchange with the FIFO does not exactly match with the ingress of orders coming in with the limit order queue at the exchange, right? So in fact, that difference in the input at the exchange is in fact the room that you have to improve the performance of the exchange server, because you can select those orders that are more likely to be matched while keeping that sequence the same, okay? So there is kind of the key idea here is to separate the critical from the non-critical orders using the mid price. So critical orders are those that are closer to the mid price. So the details of how we do this are in the paper. So please take a look. Okay, so moving on to how well does this really work. So the key questions we want to ask are, does Onyx deliver a low overall multicast latency? Does it provide inbound and outbound fairness? And does it really scale? Okay, and in terms of looking at multicast latency. So here we plot the distribution of the multicast latency of different systems. So here we can actually see that the curve on the leftmost, the Onyx, is actually provides a much lower multicast latency, closer to a few microseconds in this case with 100 participants over a commercial service, AWS gateway. And DU, which is direct unicast, effectively asking the exchange server to directly send one-to-one messages to each market participant. In terms of fairness of delivery, Onyx, so H here represents the hedging factors. So for different hedging factors, the more you hedge, kind of the fairer the delivery becomes. So we can see that actually Onyx is able to do much better with hedging, and even though CloudX is able to give you really good delivery fairness, its latency is actually not as good. Onyx is able to scale in terms of providing low multicast latencies up to 1,000 receivers. So in our experiments, actually every market participant is a single VM, but in principle with isolation, you can run multiple market participants in a single VM. So we think that this result is sort of a kind of a lower bound on what you can achieve. And we also show that the limit order queue can gracefully handle bursts. So, so to conclude, we believe that the kind of takeaway of this work is that building financial exchanges in the cloud can be realized, and you can, in fact, scale them to a larger number of participants. You don't need specialized infrastructure. But of course, you have to be willing to give up certain fairness and performance guarantees, so you need to relax them. And these exchanges provide a new operating point in the kind of curve of cost and performance. And this is something that could be an attractive option for certain kinds of exchanges. And one interesting kind of conceptual takeaway is also that doing scheduling at an application with an application-specific policy can, in fact, have a significant beneficial impact for those applications. Okay, thanks.
Thank you. Questions? There's one there.
Thanks for interesting talk. I'm just curious for the inbound fairness case, when is the timestamp written at the client side, and how can you make sure the timestamps sent by clients are genuine, not manipulated?
Right, so there's various trust models to run this system, but we kind of, so this is also assumed in prior work, that there is an entity that is, could be, for example, the SmartNIC at the client, or it could be a program that's effectively running the market participants' code that's actually giving you a trusted timestamp of order generation. So this is actually, so we have a discussion of the trust models also in the paper, but I guess the system, it is a requirement for you to have these trusted synchronized timestamps for you to be able to then order them and do various things with them. Yes. So yeah, so there are many options to kind of how you want to generate those timestamps.
Okay, thanks.
Next question.
Hello. Here.
Oh, hi.
Very cool work. Thank you for the presentation. I just had a question about transparency, right? Like in the traditional data center, there's the glass floor, right? Like you can follow the cable from your VM and like make sure it's not a bit shorter. Do you have any mechanism that does that, but in this setting? So like a way for a participant to not only trust the data center, but actually verify that the latency it gets is not worse than the others?
Yeah, that's a very interesting question. Yeah, we haven't necessarily thought too deeply about how you would provide those kinds of metrics, but I can imagine kind of the same way in which we, say, measure parameters across different clients or on the internet and try and compare. Like there might be some sort of a collaborative approach to actually doing that. But I do think it's an interesting open question, like what are good ways to ensure when anyone sees this kind of a deployment, like for everybody to be convinced that it is fair. So I think, yeah, we haven't thought too deeply about that. But I would also encourage you to pose this question on Slack, because I believe the first author may have other things to say about it. Yeah,
awesome.
Thanks.
Thank you.
It's a good question. Thanks.
Next question. There is one.
Yeah, hi. Thanks very much for the talk. Very interesting. So you're using multicast to get fairness on the market data. So what kind of loss rates do you see on multicast, and how do you cope with that?
So if I understand the question correctly, how do we implement multicast?
Well, how are you dealing with loss in multicast?
Right. So I guess the slide deck may have changed, but all right. So each of our proxy nodes is a VM that is under the control of the exchange. So if you think about this topology as a network, effectively now your proxy nodes run code that can consume a piece of data from like the parent in the tree and then duplicate, kind of make a few copies and then send it down to the children in the tree. So it's all, yeah, you should think about it as, I guess, packet processing that's implemented in software. So it's not, it does not require hardware support for multicast, if that was the concern.
Okay, so you're not doing multicast over the wire anywhere. It's all. Is it? Where is the multicast part in that case?
So if you remember the tree in the picture,
Yeah.
right? So the tree is basically sending out duplicate copies of the same piece of market data. Like every node in the tree receives one copy of the data and sends out k copies if there are k children in the tree.
Okay, but is it lossless or is it lossy?
Oh, is it lossless? No, so we run TCP between every node in the tree. So yeah, as long as there is some path, it will be lossless. However, losses do happen, and it is something that can degrade the guarantees of fairness in the system. Like if, for example, if you have no reachability between two nodes in the tree, or if so let me take a step back. So for outbound data, like the market data, so that actually runs over UDP. And so there are special services that actually do retransmissions for the outbound market data. For the inbound side, we run TCP. And that, for the most part, you can assume is lossless. So losses can get in the way of these fairness guarantees. But the measurements, at least that we've seen for these popular kind of public cloud providers, is that the loss rates are actually really low for this to be still practical in most cases.
Thank you. Thanks.
Sure.
Do we have more questions? No? So in interest of time, thank you very much.
Thank you.
Srinivas. And we go